Okay, here you're asked to describe the x values in which the function is differentiable. So we had just finished looking at 3 situations in which it's not differentiable. So now we want to know, where is it differentiable? Okay, so when you look at number 1, you'll notice that at x equal positive 1, your graph is not continuous here, because that's where you have that jump in your graph, because of this being a piecewise function. So if you remember, one of the situations in which a graph would not be differentiable at a particular point is when it's not continuous at that point. So we can tell, as I've already said, that this is not continuous at 1, at x equal 1, therefore it's not differentiable at x equal 1. A couple different ways you could write your answer in interval notation, but what it has you to do in the examples in your homework is just to express it this way. F of x is differentiable everywhere except x equal 1. Like I said, you could do this based on interval notation, but this is how they have you to do it here. Okay, number 2. If you'll notice, at x equal negative 1, that's where you have your sharp turn. So if you remember, that was one of the other situations in which a graph would not be differentiable at that particular point. So here you would say f of x is differentiable everywhere except x equal negative 1. Okay, third example, where your graph would not be differentiable here would be at positive 2, and that would be because it's not continuous at x equal 2, because that's where you have a vertical asymptote. So f of x is differentiable everywhere except x equal 2. Okay, now we're going to look at what's referred to as the alternate form for the derivative. Okay, when we're dealing with this alternate form, of course, as you see, you still got your notation here. It is still derivative, which still involves a limit. But our limit definition here is a little bit simpler than what we were using earlier, but 95% of the time you do have to use the earlier definition instead of alternate form. When you get to your homework, when you use your alternate, or when they want you to use your alternate form, they actually have it in a separate section of your homework that specifically says in the instructions to use the alternate form, so you won't have any confusion as to when you need to use this. Okay, so as it states, the existence of the limit in the alternate form requires that the one-sided limits exist and are equal to each other. And some of the problems we're going to look at, we're not going to actually have to break it into one-sided limits, because we're just going to know that they are going to exist and are going to be equal based on the fact of what kind of function we have, and because of that we can just do it based on the two-sided limit. Okay, but there is one situation where we will have to break it into the individual. Okay, so here's our first example using this alternate form. All right, so your function is x times x minus 1, and we're looking at this specifically at c equal 1. Of course, again, c is just representing some x value. Now, this function, of course, is the same thing as this. Like if you were to distribute your x right here, this is your function. Now, this is just a polynomial function. Now, if you think about the graph of a polynomial, if you remember, it does continue to infinity and negative infinity forever, but it'll have what I refer to as hills and valleys. But all of those, when I refer to hills and valleys, if you remember, that's nice rounded tops. So the top of the hill is nice and rounded, the bottom of the valley is nice and rounded, which means there are not going to be any sharp turns. A polynomial function, as I said a while ago, is continuous from negative infinity to positive infinity. There are never any interruptions in your graph when it's a polynomial. And you're not going to have vertical tangent lines. I mean, it's just this being a polynomial, you don't have to worry about any of those three situations that would keep it from being differentiable. So because of this, we're actually just going to, I mean, we're still going to use the alternate form, but we're just going to set it up and write it out as if it were just a one-sided limit. Okay, so what we have here is we're looking at this derivative. Of course, our c value specifically is 1. So we would have the limit as x approaches 1. Now, the numerator starts off with f of x, and f of x is just your function. And then you subtract from that f of c. So that means that you have to take the 1 and substitute it into the function. Okay, so if I substitute 1 into this function, and that's all divided by x minus c. Again, c is 1. Okay, so let's simplify this. Okay, so I've got the x squared minus x. Now this is going to end up giving you 0, and of course minus a 0, you wouldn't even have to write any of this portion of it down anymore, meaning this is the only thing that's left in your numerator, divided by x minus 1. Now if you did your direct substitution right now, you would actually get your indeterminate form of 0 over 0. So going back to what we know about indeterminate forms, I need to do some work to this so that I can take my limit. You can do some factoring. You have a common factor in your numerator of x that you can factor out, and therefore your x minus 1s are going to cancel. So that just leaves you with x. So now doing direct substitution, you're just going to substitute in 1, so therefore that is your answer to this. So this is, of course, when we were using the other form last, we were always ending up with just a general expression that would represent the slope of our tangent line. But see, now we're going back to looking at it at a specific point. And because we're looking at it at a specific point, we are going to be coming up with a specific answer and not just something that's general.